beginning. And first little bit of information. I'm going to be using, we'll get back to the Welsh Hole PowerPoint, but on your Blackboard, you can, and you'll see it obviously since I'm recording this, we're going to use this and this as we do this thing, the chemistry stuff. That's there. Notice periodic table. My colleague put that up. I barely assisted him because I have no talent. You'll attest to that. He did the work. I basically was a holder. And nevertheless, that's where we are. So you'll see that particular PowerPoint that I'll be referring to. And let me get to it, even though that's not the slide we want to have. Let's back up a bit. Reason is I think the graphics are very clear, and more importantly, I'm used to it. So I think it carries it in a very nice way, even though we looked at some of this stuff already. I'm going to start from the beginning. I don't necessarily use the animations here. This is the PowerPoint that has, this is the textbook has wonderful animations when we get to the cell and we start talking about resting membrane potential, which is extraordinarily important, and how muscles work and nerves work. They really have very, very good animations for that. So keep posted for that. Nevertheless, here we go. Yeah, we're made of chemicals. Okay, and everything about this, chemical signals play an extraordinary role in basically everything we do. They're there. So we have to understand the chemicals and moreover, understand the structures that are made out of chemicals. So it behooves us to have a little basic review of chemistry that's there, which I'm very fond of. And that's a nice periodic table because, and hopefully you'll be able to see it fairly well. And I'll figure out what to do with it. Maybe I'll make some pictures up for it, if we have an exam and everybody can have one of those to refer to. Easy enough to do. It's not particularly problematic to get that done. Nevertheless, I can have the print people. So we got to look at the basic chemistry and then subsequently the biochemistry. PowerPoint A really deals with the basic chemistry, chemical bonds that are so important. And the second PowerPoint, we really get into the biochem, which effectively is basically the four groups of carbohydrates, lipids, proteins, and nucleic acids, as well as nucleotides. So we'll look at all of that. And this is matter, but we talked about that before: mass, space, weight because of gravity, and it can be anything. Okay, and solid, liquid, and gas, and don't worry about those definitions. They're not going to ask you changeable shape and volume for gas. Don't care. Solid. Okay, energy. Again, these are base definitions just for you to understand. Okay, it doesn't have any of that stuff. It's all about energy as a currency that we utilize to do everything. And again, energy, there's a finite nature to energy. And effectively, again, as you'll see subsequently, ignoring that, two possible states: kinetic energy or potential. Either we're using it or we're storing it. Effectively what that means. Kinetic energy, energy, action, and potential. Think of energy that has the potential to do work and we're using it kinetically, it's working. Okay, and again, we can transform it from potential to kinetic, and again, we can release it, etc. But the trouble is, every time we make a change or a transformation in energy, and that's why I use the term, when I talk about metabolism, I talk about energy transformations, we're going to lose a little bit of that energy in the form of heat. And maybe the heat can do some work. It's just like when we have inflammation, where we are, we're generating a certain amount of heat that's there. We may be activating things that we'll learn about called pyrogens, pyro for heat, gens for generating, and they will accelerate biological processes that facilitate our healing up to a certain point. People have a misunderstanding of fever. So different kinds of energy. We look at all of these because they're all part eventually of our understanding, if not in this course, in the next, in the follow-up in AP2. Storing, and we've spent an inordinately large amount of time because it's so important to understand chemical bonds and how the energy is stored. Electrical energy, we have to look at that because really that's where the ability to send signals and then translate them into various kinds, because effectively our brain is interpreting signals in the form of electrical energy. How did they get there? And so and the fancy term is called transducing. So we're transforming one form of energy to another, and again, losing a certain amount of heat. You're hearing my voice. Mechanical energy is somehow magically being changed to electrical energy, which is eventually sending a signal to the appropriate area of our brain, which you'll come to know as the temporal lobe. See, now all those anatomical terms, now we can use them, to the temporal lobe, and we're interpreting it based on the signal. We identify it, listen, we associate one thing with something else. And there's the mechanical energy, again, moving our eardrum, and then various kinds when we look at heat and light and the aspects. Maybe that's the more complicated ones, I would think, that are there. And so we're going to look at the electromagnetic spectrum. But the gentleman who helped me put up that is our resident physicist. So if you've got a question, I'll direct you to him, and I'm sure he'd be happy to answer it. And I'll just give you what I know about it, which is limited. I don't really do physics. I don't do plants, and I don't do teeth. Everything else I'm good with, economically, physiologically. It's okay. We all have our limitations. So again, it's inefficient, lost its heat, which can be usable energy. That's all. So every time we do something, there's a certain price to pay, and that price to pay is the loss of that energy in some way, shape, or form. And now we get to the chemistry part of the program. Aha, the periodic table is upon us. So that's a periodic table of elements that are composed of atoms. Those are the first signs of identifiable matter because they have a consistent combination of protons, electrons, and neutrons, if indeed they have neutrons. More on that in a second. So they can't be broken down any farther without necessarily losing that particular identity. It's sort of the reverse of emergent properties, if you wish to think of it that way. I don't want to buy one, get one in fresh time. So I like fresh time. So again, like I said before, the big four: carbon, oxygen, hydrogen, and nitrogen, the so-called major elements. And then you're going to get to what they sometimes refer to as minor elements or additional elements. There's, depending on the author, will have a different name. And then the trace elements. Okay. And they'll give you that in a thing. So again, they're made up of atoms, unique building blocks, I want to call them that. Smallest particle, which has the properties, works for me. And again, we're good. This is why I want to state, well, I didn't see necessarily in the other text, the importance of both physical and chemical properties, because we have to understand those. And I'm sure you had this. That's what the periodic table about, to understand the language. So they have an atomic symbol. The table is constructed based on what's called their atomic number. That's the number of protons. And then the atomic weight or mass, and I'll inevitably use the terms interchangeably, which have to do with the combination of protons and neutrons. Those are the agents that have, or the particles that have mass associated with them. And therefore, they're really where we judge the weight, so to speak, or the mass of that particular atom. Understand the electrons do not play a role. Yes, there's mass, but it's so negligible, we ignore it. And then, and a lot of, as you can see, coming from the Latin, back in the old days, people going into medicine or into medicine-related fields, they taught Latin in high schools. I don't know if they still do that. Anybody have a high school that taught Latin? Good. I'm surprised. I didn't take it. I took 7 years of Spanish, 2 in junior high, 3 in high school, and 2 in college. And it wasn't until the last term of college I actually could speak some Spanish. Do not have the gift. Don't. My eldest has that. Don't ask me. So, and you can see the names. You don't have to know the Latin derivations. Voila. Here's the chart. You don't have to know the numbers. Just C, H, O, and N. And then, like I said, in us, it's calcium and phosphorus. When you take micro, it's sulfur and phosphorus. It's just a little bit different. And they all, and these all have very, very important roles. I mean, even now we're getting down here to effectively what would be considered trace elements. When you start getting, but iodine and iron are extraordinarily important. You're going to learn about the thyroid. I mean, everybody by this time should know that iron is the critical piece that makes hemoglobin. And the big problem that a lot of people have is iron deficiency. And then all of these, at least by this textbook, are, and we need little bits of these, and most of them work to make the things that make our bodies go, which are called enzymes. They're the ones that make it easier for reactions to occur, and most of the time they need a helper in the form of a trace element. Thanks for that. Everybody get it on this side? Yeah. So, got to get everybody in here. Let's see, 4, 9, 11, 14, 19, 22, 25, 27, 30. Pretty good. Voila. I'll get up in a little bit when I'm able to. Protons, positive charge, and they don't ask me what a mass unit is. I don't know. Just think of it as a unit. I'm sure someone has calculated it, but it's way beyond my pay grade. Same thing with neutrons. It's got the same atomic mass unit, but no charge. And then lastly, electrons, negative charge and virtually no weight or mass. Okay, we all knew that. And always, for our purposes to start, until we start looking at something called ionization, be either loss or gain of an electron to make a more stable thing, it's all about stability. When you're looking at these, it's all about how they are most comfortable to be with in nature. And all of that has to do with the number, and we'll get to the orbitals, the number of electrons in the outermost orbit. You've probably heard all this before, but and this is really an opportunity to understand the relevance of it. It is so critical to understand. It's really whether or not they're going to give up an electron or receive an electron. It's a concept called valence. That's the number that's involved. So when you hear the valence number, really it's really the number of electrons that have to be lost or gained to make something that's relatively stable. That's all it is. And so biologically, we seek for things that are unstable. Sometimes we can't avoid instability. But you'll see as we move on in this whole semester, the problem is when things are unstable, they tend to cause damage. And interestingly, nothing more than unstable forms of something that without it, you are going to die, called oxygen. That's really a critical piece to understand in what are called aerobic organisms, which we are, air breathers. In aerobic organisms, you've got to have oxygen. Trouble is, by utilizing oxygen, we create unstable forms, and we have to find a way to deal with it. Okay, basic stuff here. So atoms are electrically neutral in their atomic state. Protons and neutrons are found in the quote-unquote, it's the same concept of a cell. So we have a nuclear area in the atom itself, okay, and the electrons orbit around it. Nothing you haven't heard. We're going to talk about the orbitals, basically something called the octet rule. First two, there's only two, and after that, it's numbers of 8, and we are not going to go crazy over some of the stuff. Like over there on the periodic table, colors are useful. Okay, but all those guys in yellow are called transition metals. They have additional orbitals called d orbitals. I mean, all that stuff. I'm not going to get into s orbitals and p orbitals and d orbitals. Years ago, I used to know that. But what effectively happens is they can either gain or lose a number of electrons, and that's what we make. So they transition. They're very, very interesting and very important. Okay. And a lot of them is where we find trace elements that work with us, like the nickel or the iron and things like that. Really important. So historically, there have been different ways to do these planetary models and orbital models. Doesn't matter to me. We had cloud models, and the reality is for students to understand, I think we look at orbitals, useful for illustrations. The hardest thing for you folks, I think, to really get is everything we present here is on a PowerPoint, or on a whiteboard, or blackboard, depending on who wants to write on it. It's very two-dimensional. And living things are three-dimensional. You have to be able to think three-dimensionally. It's called spatial relationships. It's like those things you took on like different kinds of tests where they'll show you like a geometric figure, and in one position, and you look at 3 more or 4 more figures and figure out which one it is. It's not easy to do. That's very helpful for people who go into living fields to begin to understand that. Okay, scientific fields, that was a big deal to try to be able to visualize that sort of in your mind's eye. That's an expression I use. I don't know. Again, someone provide me with a list of modern expressions that I can communicate to you. It was only yesterday my wife told me I was an old fill in the blank. Okay, so orbitals, okay, where the electrons, and for years we had different concepts about it. It has to do with stability of the electrons and how they go around. And again, we're going to look at the outermost layer. I think it's probably using, the old days used to call it a cloud theory, but now shading it is where it's most likely to be found. It's not like they're magically in one place and stay there. Okay? But what will be very, very important to conceptualize is the idea when they're not positioned, if they're positioned irregularly. Everything, when we start looking at biology and we look at the human body, everything is about symmetry. So how many times have you seen somebody, and football season is upon us, when they look on the sideline or in any type of sport and they're doing a neurological exam, one of the things you start looking at is symmetry. If you're going to do a concussion testing, is one eye fixed? Is one eye dilated, or one eye contracted? Is the pupil constricted or dilated? And you want to look at the symmetry. Are they irregular? Do they do it at the same time? Is one side sluggish? Is one side overly fast? It's everything. Grip strength. Okay, grab my hands. Grab them as hard as you can. Is that as hard as you can do it on this side? And you're beginning to understand where the problem is. We have to look at symmetry. And it's not a whole lot different when we get down to the basic elemental thing. It's symmetry. How things look. Again, when I do these talks or these lectures, whatever you want to call them, I'm just kind of going with what I think are the important things that down the road you'll put the package together. It's not easy because you're, comparatively speaking, in the infancy. Some people less so than others, had more background with it, and that's to your advantage in the early days. So orbital shading in the region, useful for predicting. I'll help it. Voila. So you could do it like this. They're just showing you this happens to be helium because you have whatever the colors are, the red are the protons and 2 neutrons that are there. And this is that first, if you look on the far right side, as you're looking at that whiteboard to the side, you see the so-called ideal or Nobel gases. Okay, helium, neon, argon, krypton, xenon, radon, and whatever that last guy is. It's been a long time since it's only been 50 years since I graduated with chemistry. 52. Too specific. But nevertheless, what they're showing you here is those 2 electrons. We used to think electrons paired around. Oh, they always travel in pairs. They're just inherently more stable, typically, if they're in pairs. That might be the way to look at it. But what it means is there's an equal distribution. That's a good way to look at it. Not necessarily they're in pairs. And you're going to see even on these PowerPoints, a lot of times they're messed up. Whoever was doing the artwork or had the artwork done was trying to depict this. So, I mean, both of those, whatever works for you. Well, it's all about, and because of that, effectively, this has very, very limited, if any, chemical properties. We have to really do something to live. Inherently, that's chemically stable because those outer electrons are happy the way they are. Leave me alone. Basically, I'm happy. As opposed to, almost everything else that has some degree of reactivity. Physically, there are properties. So helium, lighter than air, physical property. Neon has this remarkable capacity when energy is passed through it to provide a certain amount, whatever happens to those energy levels, we begin to see with those electrons, we get neon lights. I mean, things that in the old days, there were all neon lights. Now we have LED and things like that are changed. In the old days, it was like, you still see the same thing. You end up in Las Vegas, all these extraordinary, it's daylight in the middle of the night. There are no clocks there. They don't want you to think about time. To try, but different kinds of properties. Argon, krypton. Radon's very interesting in and of itself. Okay. Radon is one of these gases that are there. Interestingly enough, it has a physical, I'm not sure how it does it to qualify it, but I know when we sold a house that we lived in O'Hara Township, for those folks who are familiar with the area around here, a lot of the areas around Pittsburgh were basically strip mined and filled in. They were looking for coal, they were looking for mostly coal. And the trouble is when you do that, you release a certain amount of stored gases. Radon is one of them, and radon, if it's stored long enough, has the ability to be carcinogenic. Exactly how that works, I don't know. So we had to do a radon test in our garage, in our basement rather, when we were selling the house. And it found out we had a level. Little did we know we had the house for about 10 years, and we moved to a different house, same school district. But because that was there, we had two choices. We could lower the cost of the house, the price of what's called radon mitigation. We either had to mitigate it. Listen how they do this. They take like an exhaust fan in your basement, run it out to your roof, and spit the radon out there. Why is that safer? But that's part of it. Or we had to reduce the sale price $1,000 versus $1,000 to it. Back then, that was the better part of 30 years ago. So it's interesting. They're not all necessarily innocent. And believe me, if you have a home around here, that's going to be part of, you're going to have radon detectors and different detectors that you need to have, particularly in an area where there's been mines have been filled in, which is most. Nevertheless, hydrogen's the oddball. Why? Only has one proton, no neutrons, normally. It's the only one that doesn't come with neutrons, normally. Why am I saying that 6 times? Because now we begin to understand the nuance of the periodic table. They're not always the same. As you can see, lithium. It's not always 2 and 2 or 3 and 3 or like carbon 6 and 6. Sometimes there's different numbers. That's taken into account. So as you'll see, we have the atomic number, which has to do with the number of protons, the mass or atomic weight or atomic mass, whatever you want to call it. If you're not sure, you have the luxury on a test to ask me those kinds of things. Hopefully I would have them clarified. That's the number of normal protons and neutrons. And so that gives you atomic weight. And then there's this bad boy, isotopes. We talked about carbon-14. That's an isotope. It happens. So what you see on the, here, hydrogen, 1.08. Not one, there's only one proton. There's no neutrons. Why is that? Because in nature, we have neutrons. The average atomic mass, and it's true for all of these. Everything. In the occasional really oddball, really. I mean, I'm not familiar with why that has that, but that little extra number tells you things. That means that there's a certain number of variations that we see. Potassium, okay, normally would be, let's say, a different number, let's say 39, or sodium might be normally 21 or 22. That's because all of these atoms have variation in the form of neutrons. Even hydrogen, which ordinarily doesn't have any. So here's hydrogen, one proton, one electron normally, helium, lithium, and now just begin to see their properties that become fairly obvious. And eventually that's something that you're going to look at when we start to talk about this in length. Here's helium. So helium, we said, so it had 2 plus 2 in the nucleus and a couple of electrons moving around it, perfectly balanced. So that's the number. That first orbital has just 2, that first orbital. We're good to go. Don't do anything else. Physical properties. Hydrogen. So understand, because the number is 2 there, hydrogen normally just has a proton, we'll make that as a positive, and an electron. So there's hydrogen atom. Trouble is having that one electron is not, it needs to either find another electron or lose that one. And most of the time it does one of the two. It can either find something else to bond to, let's say another hydrogen. Here's another hydrogen, here's a proton in the middle, here's the electron, and what happens? They bond. What do we get? A more stable, so it has some very interesting properties, but theoretically more stable, H2 hydrogen gas. Apparently more stable than just a hydrogen. Doesn't mean it's a stable stable, because it's explosive gas. The helium is not. Just the class that we talked about that? You're all looking vague. Why do we know that? What event happened with hydrogen gas in 1937 in either Lakewood or Lakehurst, New Jersey? It told us that hydrogen gas was explosive. History. Without knowing history, you're doomed to repeat it, you know? That whole thing. Hydrogen gas. My mom, who was 19 at the time, said from Newark, New Jersey, where she lived for the first 40 or so years of her life, it was, she could see the light in the sky. So, and I think it was about 50 miles away. Sort of like, sort of middle of New Jersey, pushing toward the coastline. There was a dirigible called the Hindenburg. There's a lot of interesting, you want to go back and read books about it, some are fiction, some are based in limited fact, because it was coming from Germany, which was Nazi Germany at the time, and as it was going to land or be tethered down so people could get off, the damn thing exploded. Everybody was lost. The question was there something that was going on? I mean, there was a relationship to Einstein, who by that time, I think was almost on his way to go to Princeton and study, blah, 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 blah. So a lot of interesting, what I call historical fiction about it. That, at that time, blimps, or dirigibles, as they called them, were filled with hydrogen. Now, when the Steelers are the main game, which it will be 4 or 5 times this year, you're going to have the blimp. The stadium. It's got helium. The other thing hydrogen can do, and it does this a heck of a lot. Positive guy in the middle, electron over here. Goodbye to the electron. So it has a proton and an electron. If it loses the electron, over here, I put E with a minus sign, what are you left with? A proton. But another name to give this is hydrogen ion. You write a plus sign, which has lost the electron, so it's hydrogen plus. Another name, that's a hydrogen ion. A lot of times it's just a proton. We move those around all the time. In fact, that's how we derive the greatest amount of our energy from something in the Krebs cycle called the proton photophore. I'm going to get into, let me ask you about, want to see beads of sweat? I had such a headache this morning. Maybe I'm allergies. I have a spare Zyrtec in my pocket just in case. Nevertheless, moving on. So here's the atomic, and you can write it this way. I'm not going to have it written or anything like that. Number of protons in the nucleus, they use a subscript. Mass number, you use a superscript. Yeah, it's on the table. Let's see. Table is going to be up. Like I said, I'll print it out. So we're not going to play memorize the table, not this class. These are the variations in neutrons that are so significant. They're called isotopes. Iso for same, tope for type, if you want to think of it that way. Structural variations based on neutrons. Atomic numbers are the same. Mass numbers are different. Average of mass numbers of all isotope forms in an atom. So here's hydrogen. It can have 1. We call that deuterium. Or it have 3. We can call that tritium. So it's a very famous molecule. The hydrogen, normally, and we'll just, maybe I'll frame it this way. Only if I have, oxygen, 8 protons, 1 more than neutron. outermost orbital, it has only 6 electrons. So normally, and there's this oxygen, normally what it does is it wants to pick up a couple of electrons. So let's assume, for argument's sake, it's picked up 2. I'll just underline. So we have 2 extra electrons. The way oxygen typically exists is something called O with a -2 sign. That's oxygen. So what it does frequently is it combines with, well, and you're going to see this when we understand metabolically how things work, with 2 protons with hydrogen ions, and it makes voila! H2O, which you and I all know is water. That's what happens in the proton force. That's why oxygen is so important. We use oxygen gas, we divide it into its more friendly form, because with the O with a -2 sign, it picks up, and the electrons it picks up comes from that whole thing we call the Krebs cycle. And to balance it out, it picks up protons, which come from the Krebs cycle, and we get a waste product that we can excrete fairly easily. Love that. And since it all comes from organic compounds that have carbon, we take the carbons when we're done with them, and we bond them to oxygen, and we get carbon. What a country. Another waste product we can just exhale. That's the beauty of our metabolism. Okay, the organic compounds generally are easily broken down into water and carbon dioxide. Other problems don't exist now. So a lot of what we get is what we put aside, we utilize, and other bad stuff. That's water. Now just suppose, because we see it on the periodic table, we had, in the way we call deuterium, we would put D2O. And another fancy term would be deuterated. You have to write that down. Water. So we basically replace the hydrogen with its cousin deuterium. What's another name for that? You had an extra neutron in every hydrogen. What would that make the water physically? That's heavy water. How did you know that, sir? Is it a good guess? You said what? Okay. Heavy water. Why is heavy water important? Store. World War II history forthcoming. Remember World War II? I'm from the generation whose parents were all in. They all served in one way or shape. The biggest thing about World War II that was going to end it was everybody was trying to build an atomic weapon. I'm not defending atomic weapons or anything like that. It's an interesting controversial area. Obviously, we were the nation who used them to end the part of the war in Japan. But Nazi Germany was, they all had great scientists. Most of our great scientists came, Einstein escaped Nazi Germany for a variety of reasons, mostly for persecution. Nevertheless, they used that in atomic experiments because the way all the heat that's released has to be dissipated. If you used regular water, it would require immense amounts and would produce immense amounts of heat that you couldn't control. Heavy water is harder to move around, and that basically absorbs the heat more efficiently. So we tracked heavy water, which was made in Norway, on its way to a particular area in Nazi Germany, and that's where the plant was, and boom. And so and heavy water is still used. I do not know where tritium comes from, but there's a lot of relevance with these isotopes. So it was made effectively. It took regular water, knowing that an X amount of it was going to be, and basically refined it. And this plant, and Norway at that time was under the control of Nazi Germany. They had been invaded, even though there was a fair amount of resistance that was going on. It's a hobby of mine, among my other hobbies. So though those are relatively stable, radioisotopes like we talked about carbon-14, what makes them radioisotopes is that the decay gives off a certain amount of energy, which we refer to as radioactivity. And in the old days, it was easy to detect with something called a Geiger counter. There are other methods that are used today, but these and they're extraordinarily important in medicine. They're extraordinarily important in medical science because we can tag things, our bodies, those trace elements. We utilize, perhaps the one we use, something called technetium, and we use radioactive iodine a whole lot, both therapeutically and diagnostically. You can track it. Okay. And so we can detect it now. We utilize something that's a more sophisticated approach called a scanner. And you'll hear all about that, and particularly those of you who might be heading toward nuclear medicine and some of the health-related field side or health science majors, rather, you're going to become very, very acquainted with that. Okay. By the time you get to be my age, you've had some kind of scans done that involve some kind of injecting you with some type of substance that can be measured. There are bone scans, there are brain scans, liver spleen scans, thyroid scans. That's where the iodine certainly comes in, plus treating certain kinds of thyroid cancer. That's part of it. So very, very important. Same chemistry as their stable isotopes, but then they can be used for diagnosis. All radioactivity, not a lot of alls, as you probably have heard. Nevers and alls are something in life sciences we tend to stay away from because there's typically exceptions to the rule. But radioactivity is not one of it. It's a matter of how much. Okay, so we can use them therapeutically to destroy cancers, and other ones can cause it. Here's the radon that's formed from uranium decay that I was talking about, and lung cancer. So it's interesting how those things occur. So that's all, I'm trying to, give you the broader picture. We talked about this already. The idea of being combined with other atoms. Again, these are the emergent properties. Molecule, non-specific term. For two or more atoms bonded together, hydrogen. But when we talk about a compound, water. H2O, both on the board over there. Specific molecule that has two or more different kinds of atoms bonded together. You saw me write this last week, C6H12O6. That's a generic term for, I'll write it down because you're going to have to know. A 6-carbon sugar, because like a hexagon, call them hexos. Hex for 6 and O's indication sugar. 6, for C for carbon, a 6-carbon sugar. So it's basically, understand what sugars are, as we get the term carbohydrates. Equal amounts of water. You can write that. What we'll do, C, the H2O there with an N, in this case the N equals 6. The number of carbons times 6 and the number of waters times 6. And if you run through, the old distributive property, used to be a math major too. Associative, distributive, love those. Don't ask me. So molecules with only one type of atom are just called molecules. Everything else is a compound. And now, how do we put them together? I love this because this is cooking. So when we get most matter, it doesn't exist by itself. Even water, to a certain extent, the water that you and I get out of that tap, even water that you run through a Brita or a Pure or a filter, okay, is not just water. Okay, you're still going to have stuff in there that's dissolved in it, small particles that are electrolytes because they are water soluble. The water will surround them, and you won't be able to visibly see them unless they're inherently pigmented. Okay? And it's just the way it is. You can't help that. We call those solutions. Okay, I'll get to colloids and suspensions. So a solution, the biggest thing about a solution, you You can see through it. It doesn't exclude, and as I said, inherent pigmentation. It's like you probably did this in high school. You took a blob of ink or some type of pigmented material, you dropped it in some water, and the whole thing turned blue or turned red, right? Okay. It's a process of something we call diffusion, which we're certainly going to get to. But in this case, the minerals don't have any pigment, and whatever water you're choosing to drink in bottled water. What we often utilize in the lab is we call deionized water or triple distilled water. You're trying to remove as much as you can, okay? As much of the materials that may be dissolved by distillation, which is a process where we are able to basically, hopefully, extract just the water that's there. So that makes a solution. Big deal, you can see through it. When you get into microbiology, as many of you are heading to down the road, in micro, when we look at different types of solutions that we grow things in, the key is clear. If you can see through it, bacteria are not growing it. It starts to get cloudy or murky, stuff's growing it. So clear is very important. Easy. That's there. Colloid. Solute particles are larger than in the solution, and so light doesn't get all the way through. Okay? So that's kind of what happens. And it's heat related for gelatin, which makes jello. And even if it was clear and you didn't have any additional pigment to it to make like cherry or whatever jelly you're going to use, it's there. When you dissolve it, you boil the water, it dissolves, but as it begins to cool, then those molecules come together in such a way that it has a certain degree of opacity. We cannot see through it. We can't pass light through it like we can here. And even in the laboratory, we can do that with basically it's called a spectrometer. You don't have to know any of that stuff for now. In micro, you might have to be familiar with it depending on who's teaching the micro lab, but that's what it is. Our bloodstream is very much colloidal in nature because a lot of the materials in there, if you took the blood as a whole, you cannot see through it. If you divide it into the plasma, that's the stuff that's dissolved in the solution. But the red cells and the white cells and the platelets, the formed elements, settle out. And you get to this when you do the blood unit in AP2, and that's much more of a colloid. Okay? Milk is an example of a colloid. Why? Because milk has a lot of protein in it, as we know. And what proteins do is they hold on to water. They actually are, and they're very important in our bloodstream. It has a thing called colloidal, which you'll get to, osmotic pressure. It's the holding on to the liquid so it doesn't go out. So that's an example. And depending on conditions, they talk about the inside of the cell. The inside of our cell we call it a sol gel. It goes between, depending on what's going on around it in chemical reactions, it either can be a solution or it can be more like a gel. There. So it's not necessarily liquid, certainly not solid, but it's somewhere in between depending on what's going on. And here's the blood one that I was telling you about. Why blood is also a suspension. Okay. And what happens with, here's blood that's been drawn into a test tube. If we just let it sit there, we accelerate it when we're trying to do that from a blood bank perspective, and we take it for a spin. Okay. Use a centrifuge, the heavier items settle to the bottom, and voila, you have the settled red blood cells. Another name for them is pack cells. You have a tiny layer here in between. Let me get my cursor, where white cells and platelets are. And then you have the supernatant liquid, the stuff that's on top there. Fancy name in chemistry, supernatant. Don't have to know that. It's called plasma. And again, that should be, even though there's generally like a straw color to it, you should be able to see through it. It's there. What happens with milk, have you ever had spoiled milk and seen it like in a clear, if it was like in a clear bottle or something like that? Spoiled milk, the protein's denatured. It's been sitting in the fridge too long. Maybe you left it out. Basically what happens, the protein's denatured. It curdles. And what happens to it, Muffet, Tuffet, Curds, Whey. You remember her? Spider beside her. Oh, help me. Little Miss Muffet sat on a tuffet eating her. See, you remember her. And those stories we heard. curds and whey. Okay, so what happens when you're making? They take milk to make different kinds of milk to make cheese, like Parmesan cheese. Pardon me, food moment. Okay, they make that. They heat it. Okay, and what happens is that mixture at a certain temperature. Once they reach a certain temperature, they'll put something in there. Let's say they put lemon juice in there. That's acidic. So between the heat and the alteration in the pH, the proteins will begin to denature. It will curdle. And when you remove the curds, that's going to become the cheese. Okay? What's left is the whey, which still has some protein in it. And then a lot of times in Italy, they have to recook it. That's where ricotta comes from, recooked. See, you learn something new every day. That's food science is all part of this. Didn't remember Muffet and her. I use a lot of those examples. Just wait till we get to those three bears and that Goldilocks. Just watch out. See? So solutions are homogeneous, uniform, distributed evenly throughout so they don't obstruct light. So we talk about, and these are really important terms. When we get through with this unit, we start talking about movement across membranes. We're going to talk about solvent. In our case, it's water. Easy. Universal solvent for living systems. Solute, anything dissolved. Sugars, electrolytes, even proteins. Things that dissolve, those are the solutes. Stuff that's dissolved in the water. So we talk about the relationship between solute and solvent. That whole thing I talked about last week called tonicity has to do with it. Isotonic, why we have normal saline or lactated ringers are because of that. So all of those, so they're transparent, salts and sugars, even our atmosphere is different gases that effectively are dissolved. And it typically in the body is a combination of gases, liquids. If you didn't know it, we have gases in our bloodstream. We have a certain amount of oxygen dissolved in the gas, carbon dioxide dissolved within our bloodstream itself. We just do. It has to. So let's stop it there. I don't want to get into discussing why you're going to find out in science, in life science, we use percentages. Thank God you don't have to learn about molarity and molality now. Have fun for the rest of your day. We'll stop it. Stop recording.